Hello everyone, my name is Jyoti and today I will introduce the deploy a microservices system to a AWS EC2 cloud in the SystemTap project. So SystemTap is a modern solution using NFC technology to replace traditional business cards and allowing users to easily share their contact information with just a tap on their phone. The main objective of this project is to create an efficient, low cost-effective network solution that leverages NFC technology for fast, secure, and contactless information sharing. And we aim to promote NFC adoption in every business interaction, making it easier for people to connect. And lastly, we want to build a scalable and a flexible platform using modern technologies such as microservices, architecture, and Docker and AWS EC2 and GitLab CI/CD to ensure that the solution can grow and adapt to the future needs. So our tech stack include React.js and Next.js for building the front end, and the back end is powered by Python, Django, and a fast API for API development. So we use MongoDB as our NoSQL database and GitLab CI/CD automate our testing and deployment pipeline. And the Docker is used for backing services while AWS EC2 provide scalable and cloud infrastructure and engine is to ensure load balancing and security. And now in the system overview, we will cover the key components including the AWS EC2 instance, the Docker container, Docker network, and the client browser. And we will also discuss their roles interaction within the system. And now let's start with the AWS EC2 instance. So it is a cloud computing service provided by Amazon web services and that enable us to run virtual machines on the cloud. So it acts as a primary host for all our Docker container and handle various resources such as CPU, RAM, and storage. So in the system, the EC2 instance provides the necessary infrastructure for deploying and managing the Docker containers. So it manages the Docker network and ensures the scalability and high availability of our application. And it serves as a repository for data store, specifically for the app volume used by the MongoDB containers. So now let's talk about Docker containers. So a container is an application level virtualization that allows us to package an application and its dependency into a single, lightweight unit that can run on any environment. So in the system, the application service is handle all the main application logics such as user registration, logging, and authentication, and the image service is many image processing tasks including uploading, resizing, and storing images. And the backend for Serap card is provided by a API endpoint for managing the shared data. It supports a CRUD operation and WebSocket communication for real-time update. And The last one is a MongoDB container. It stores all the application data, including user information, shared cards, and image metadata. So it ensures the data persistence and consistency. So now let's talk about the Docker volumes. A volume is a way to persist data on the Docker host across the container restart, and it ensures the data durability even if the container is removed or restarted. So role in the system and the app volume store MongoDB data, including user profile, shared card information, and images. So this volume allows MongoDB data to persist and be covered in case of container or host failure. And finally, let's discuss about the client browser. So a client browser is the end user interface used to access the system via web browsers such as Chrome, Firefox, or Safari. And in the role of it, a user access to the system through a web browser, and they send HTTP requests to server container like as application server, image server, or backend for share card through a specific port. And the browser displays the data received from the system in HTML, JavaScript, or images. So now is the workflow of the system. At first, the user access the system via a web browser, and they send HTTP requests to the application server to register for an account or retrieve data. An application server receives the request from the user and check access right and request MongoDB to fetch the required data. If the required is related to an images, it forward to request to the images server. So images server is managed image relay requests such as uploading, editing, and storing offload images processing from the application server. And the backend share car is handle requests related to the share cars feature and is ensure data is secure and synchronized over the WebSocket. As a MongoDB is store data related to a user, a shared card transaction, and all the detail, and is return data to other container when needed.
Hello, my name is Chang. In this session, I will present the deployment process of our system. I will explain how we use Dockerfile and Docker Compose to manage containers and provide a live demo on an AWS server. You already know what containers are and what they are used for. You're probably wondering that what happened next. Now I will explain the process of converting an application into a container using Docker. Docker itself is an application that runs up the command line. It reads the Dockerfile, then Dockerfile reads a requirements.txt file, install dependency and run the application in installation, like uploading part of your computer to another system or server. The first time you run a Dockerfile, it has to download and install the Python runtime file for the version of Python used to create an application, but only once. If you share other containers with those same parameters, it will simply run the Python script. Next, you need to know what a Docker image. Docker images are the building blocks of Docker containers. A Docker image contains the application code, data files, configuration files, library, and other dependencies needed to run an application. You can think a Docker image as a template from which Docker containers are created and executed. Each Docker image is composed of multiple layers. Each layer represents a specific set of changes made to image, and is composed based on instruction in a Docker file. And so, how to build Docker image? Docker file specify how Docker builds the image and contain a series of commands to build the image. Each command builds new layer that become a part of final image. Let's take a look at Dockerfile for our backend application. Here from Python 3.11, this line of code specifies that the container will use Python 3.11 based image. It sets up the environment for running Python 3.11 applications inside the container, and worker/app will set a working directory inside the container to the app. Copy requirements txt will copy the requirements file from the local machine to the app directory in the container. The requirements txt file contains a list of dependencies needed for the application. Run pip install no cache the flag are requirements. This command runs the pip install command to install all the dependencies listed in requirement txt in the container. The no cache the option ensures that pip doesn't store the downloaded package files, thus reducing the image time. Copy ... This line copies the entire application from local directory to the app directory inside the container. This ensures that all the application source code and files are available inside the container. And the last line of code is cmd python manage.p run server 0000 8000. This cmd command specifies the default command to run the container starts. It runs the Django development server using Python manage.p file run server and bind it to 0000 8000, meaning it will be accessible on all network interfaces at port 8000 inside the container. In here I already accessed in Amazon EC2 server, and I will check all the image in my system. I use Docker images command. Here each image have information of repository, tags, image ID created and signed. Repository is the name of repository where the image is stored, and the tag in here is alphanumeric label assigned to make image easier to reference. It may be 4.4, 6.0.9 or use the latest. Latest here means that the current version. And the image ID is a unique identifier for the image. It is random, hard to remember string. It also have create information is how long ago the image was created and the size of the image. Next, we move to Docker Compose. Docker Compose is an optional tool provided by Docker that makes using multiple containers easy. Docker Compose allows you to define a multiple container setup in a single YAML format called compose file. YAML is a format for configuration files that designed to be both human and computer readable. The compose file communicates with Docker and identifies the containers you need and how you should configure them. The containers in a Docker file is called services. Uh, in our project, we have 4 services, include Mongo, backend, frontend, and service for image storage. But I cannot cap all the Docker compose in here. It's too long, so I just cap the service for Mongo and second tab backend. And in our compose file, we define the Mongo network as private network. For each service, the compose file grants you control over service in its config include choosing an image. In here, we're choosing Mongo 4.4, and we uh, give the container a specific name. In here is Mongo, making it easier to identify and manage. We exposing the ports, exposing network ports, zip map ports 27017 on the host machine to port 27017 in the container. This is then the port for MongoDB, and it allows you to access the database from your host machine. And in here it's mounting storage volumes. It mounting the data directory on your host machine to data/db inside the container. This ensures that your MongoDB data is preserved even if the container is stopped or removed. Now I will move to a quick demo. I will check all the containers are running on the system using the command docker ps. Yes. Each container has specific information such as container ID, image, port, and name. Here, container ID and image. The port of each service and the name we define in the container name. This is the end of our presentation.
Hello everyone, I'm Nhân and now I'm going to present about CI/CD, continuous integration and continuous delivery, continuous deployment pipeline in our project. We use GitLab CI CD for our project, and when I commit code to our remote repository, the GitLab runner will run the configuration in gitlab.ci.yml, and GitLab Runner is a Linux machine for running CI/CD pipeline, and uh, this is our CI/CD pipeline diagram. As you see, when we commit code to our main branch, the process will start to build and deploy. In our microservice system, the many service and the CI/CD process will be more rigorous. Uh, so so the process consists of 3 stages: unit testing, image building, and AWS deployment stage. And in other repository, the pipeline consists of just 2 stages: is building building container, building Docker container, and AWS deployment. And in our compose repository, uh, your repository is just for deployment by Docker Compose, and Huyền Trang explains this part. The pipeline has only one deployment state, and because in this repository we just need Docker Compose file, and we don't need to build any new image. We just implement deployment state uh, for AWS. And if if we change uh, and if we change the process in CI/CD or change the Docker Compose deployment method, this second tab compose, it consists of GitLab CI and Docker Compose .yml uh, .yml file. Mm, and if you change the process in CI/CD or change Docker Compose deployment method, the AWS instance can continuously deploy when we change the Docker Compose file and commit. And here's our unit testing state. Let, let me open the second tab B repository and this GitLab CI. The in the unit testing state, we will install Mongo. We will install MongoDB and set environment variables. And we install some tools and dependency. Um, uh, and run migrate and run migrate for and unit testing by the command python manage.py test. Your second state is in our CI/CD pipeline is image building state. In this state, in this state, if we commit our code to default branch, the GitLab runner will log in to the GitLab Docker registry by docker login registry.gitlab.com. Uh, mm, and build a Docker image by the Docker file. In the previous part, Huyền Trang explained about the Docker file, and uh, we will run the command docker push to push it to GitLab registry, and this is our container registry. It consists of four images: B circle, second tab email img, second tab fe, and second tab b. And after that, the last state is deployment state. When the image mm, when the image is pushed into uh, is pushed to registry.gitlab.com, the GitLab runner will get our AWS key, will get our AWS key and add it to our uh, to our AWS instance, and cd to second tab compose. I will navigate to our instance, cd to home folder, and ls. Now we prepare a second tab compose local repository uh, in our AWS instance, and the GitLab runner will run cd uh, to the repository second tab compose, and run git pull for pulling the latest image, uh, pulling the latest uh, um, latest version of second tab compose repository, and run docker compose pull and docker compose up docker compose up to deploy, and prune image. Now now I now the system is deployed, and I can run docker ps. We can see um, the docker containers is running, and as you see And as you see, um, the front end the front end container is running on port 3000. uh, but we want to uh, but we want to run it in port 80. So the next part Phương will present about how we Phương will explain about how we use engine proxy to run our application on port 8 on port 80 and set up the domain the domain our for our system. Thank you.
Afternoon teachers, my name is Nguyễn Hà Phương and in this presentation I will focus specifically on the proxy and domain configuration. Well, this involves how we do the Nginx as a reverse proxy and set up the DNS for rotated traffic seamlessly to our applications. Let's start with the Nginx reverse proxy. The Nginx is a high-performance open source web server and reverse proxy server known for simple configurations and low resource consumption. It has become a popular choice for serving web content due to its ability to handle a large number of concurrent connections. Well, to make our app, which is run on the port 3000, accessible over the standard HTTP port 80, we configure the Nginx as a reverse proxy. This setup will hide the internal network from the user and ensure the better performance and security. Here is a simplified diagram that when the user access the internet, their request first go through the Nginx proxy. The Nginx then forward it to the web server, which is running inside our Docker container on port 3000, and response to the server will follow the reverse path back to the proxy and to the internet, so the user can see it. Now let me show you that the actual Nginx configuration code. While the key part here is proxy path, which forwards income requests to our app running on port 3000, the additional headers will ensure proper forwarding of client information, which is useful for logging and security. Next, let's talk about the domain configurations. We use the custom domain techcase.online for our project. To link this domain to our AWS EC2 server, we add a DNS record. The host will be .techcase.online type A value 3.265.195.130 for the public IP of our EC2 instance, and the time to live is 30 minutes. Well, this means that when a user type techcase.online on their browser, the DNS result is to our EC2 server's IP address. The engine is listened to the port 80, then forward the request to our app running on port 3000. And by combining this domain setup with the reverse proxy configurations, we ensure a seamless user experience. The user access the app without knowing anything about the internal setup. During testing, we evaluate the system performance under various loads. Firstly, about the response time for 100 concurrent requests, the average response time was 250 milliseconds. With 500 concurrent requests, the response time will increase slightly to 450 milliseconds, which is still under our target of 500 milliseconds. The throughput with 100 concurrent requests that the system can handle is 200 requests per second, and under 500 concurrent requests, throughput drops slightly to 150 requests per second, but it can remain stable. Resource uses are the CPU peak at 75% and the memory uses were at 60%. This metric demonstrates that our system with the Nginx redundancy is robust and efficient even under significant load. And here are some of the key achievements from this project. By using the Docker container and Nginx, we achieve a scalable and manageable infrastructure. Also, the system can maintain excellent performance and stability during load contests. And we're also successful in deploying an advanced backend system with minimal resource, proving that even complex systems can be affordable. And now I will quickly demonstrate how everything works. So this is our website. Let's go to the tickets.online. The website will require you to log in the page using the Gmail, and then you will see this interface. So the first thing to do with this is to create a new card. Then we click to the card and modify the information in it. So in this card information, we can modify the profile pictures, name, the slogans, and then add our media link. I have created a sample card with fully information for me, and then I can press the save informations and the information will appear in the card. So I have my information done here. So after I saving the information on the internet, the card will receive the same information as the website. So I can use the physical card of mine to like exchange it with my friends with only one touch. So this is the end of our presentations. Thank you for listening.